Okay, so now let's get started with the finals review. So any questions before we start with that? Yes, guys.
So is it accurate to say that this is a way of mapping your data into another space that you can run gaming from?
Yeah. K-means. Well, yeah, so once you run k-means, you just get labels then, right? Saying, okay, this point belongs to, is this cluster and this is that. And then you can color the original points with that color. Yeah, so that's fair to say. All right, so what was I doing? Okay, so on Piazza, I have posted like a list of topics that we have covered and things that could be asked in the exam, right? And where is that? Topics, here it is. Pin it. All right, so let's sort of, so I would suggest that after this class you can look through these topics. Clearly 79 people have seen it. But, so these are the different things we covered, and then these are different questions that I could base the finals questions on, right? So just quickly going through that. So we did linear regression first, right? So there was a big chunk of our discussion on linear models, and the first linear model we looked at was linear regression, right? So the one thing that you want to understand when you do your review is, okay, how is the learning done, right? And if you remember, there were two ways we discussed it. One was sort of this error minimization, where we said, let's pose this optimization problem as a problem in which we are trying to minimize our squared loss between what you predict and what the actual value is. And then we do gradient descent on that, and or actually we were able to find the exact expression, right? We could derive it. So do look at the derivation as well. So how do you derive the exact expression? And then we said, okay, we can also do sort of a gradient descent approach. There's one small discussion on what does bias term do, right? So if you remember, bias lets you not force your lines to go through the origin. So if you do not have bias, right, then your lines will always pass through the origin, because you'll say y is W transpose X. So if all your x's are 0, then W transpose X will be 0. That means y will be 0, right? But if you do, but sometimes, or in most cases, you do not want your line to go through the origin. So that's why we incorporate a bias. And so in your problems, in gradients, whenever I've given you, I've explicitly stated that there will be a bias, right? So make sure that you read the problems properly. And the other thing is also where you put the bias. You can put that number 1 in your data in the beginning or in the end or in the middle, wherever you want, right? But the thing that will change is that now when you get your weights, the bias weight will be in that place. So that's the care that you need to take. Usually, just to keep it simple, we put the bias at the front, right? And then go from there. So that's another thing. One more thing that you want to sort of understand is this basis function expansion, which kind of ties to the kernel methods discussion, right? So if you want to learn nonlinear curves instead of straight lines, one way to do it in linear regression is by doing basis function expansion, which is you take your x and you apply bunch of basis functions to it, and each basis function is nonlinear, and that's how you get like a curve, right? And then we also talked about the fact that regression in its plain vanilla form is susceptible to outliers, right? Now, how do we handle it is by doing something called robust regression. So in robust regression, what we do is that instead of assuming that our error is a squared form, we assume that error is an absolute value. So y minus W transpose X, an absolute of that, right? And that lets you, the way it helps is that it does not penalize your solutions as much as the squared loss would do, right? So make sure that you are sort of comfortable with this part. So let me quickly look at what problems we have done in this. I can get to. So the quiz that I posted is called Finals Preparation or Finals Practice. All right. Let me see which ones are about linear regression. Aha, this is something that you just did, right? So here I give you some data, right? And of course, see, in linear regression, the learning part involves computing an inverse, right? Because it is x transpose x inverse x transpose y. That's W, right? So I would not give you a very big problem to solve because computing inverse is not easy. But you can compute inverse of a small matrix. You can compute inverse of a 2 by 2 matrix. So this is the finals review, part 1, right? So remember that the solution for a unregularized is this, right? Now clearly if I give you some data, so you have to compute this part, right? Now x transpose x will be a D cross D matrix. It will be hard to compute an inverse of that. But what if x transpose x is just a 2 by 2 matrix, right? You can compute inverse of that, right? Because that is just how do you compute inverse? AD minus BC minus AD, I don't know. Oh, I forgot how to do it. But I think it's sort of a standard way to do that. So I could ask you that, right? And if I ask you that, I'll tell you how to do it. So don't go back and start saying, okay, how to compute inverse. But the idea is that don't get sort of intimidated if I actually want you to compute inverse, as long as it's 2 or 1. What if x transpose x is just 1 cross 1 matrix? Can that happen? That could happen if you only have one-dimensional data, right? There's no intercept, it's d by d. So x transpose x inverse in that case will just be 1 over x transpose x, right? So that is easy. So those kind of things could sort of are fair game. All right. Now in this problem, what I want you to understand is that this is more of the probabilistic interpretation, right? Where we are saying that W is a weight vector and Y is a random variable, and every Y is essentially a Gaussian random variable centered at W transpose X. So the mean is W transpose X, and there is some sigma square, right? And in this particular problem, I've given you what sigma square is, 0.01, and then I give you different W's. So all I want you to do is find out what is the log likelihood of my data, right? So whenever we say, okay, compute the log likelihood of something, anything, the first question you should ask is, okay, what is the probability distribution for that value, for every random variable? And as long as you know what that is, then you can just compute a product of that. That gives you the likelihood, and if you take a log and then do a sum, that gives you a log likelihood, right? So that is general idea. Any questions about this particular problem or this topic? Yeah. Posterior, right? How to compute the posterior, right? So this question is about Bayesian linear regression, right? So here we assume that even our W is a random variable, right? So what we do is, so you want to brush up on Bayesian linear regression, and most of it is same as linear regression, right? So we assume that Y is a normally distributed a random variable with mean W transpose X and some sigma square, right? And of course every Y for all I. So let's say you have some data set, right? So that's you have x1, x2, x3, and then y1, y2, y3. And then what you assume is that W itself, right? So W is your weight vector, is also a Gaussian distribution with some mean and some covariance matrix. The reason I'm writing a covariance matrix here is because W will be a vector, right? That will depend on how many features you have. So let's say you have D features and you add one intercept term. So W will be a D plus 1 cross 1 vector, right? Which means that if I want to model it as a Gaussian, I will have to model it as a multivariate Gaussian with some mean vector and some covariance matrix, right? Now if I want to compute the posterior for W, so we can compute the likelihood for my data. So in D, let's say this is D is my data set, right? So likelihood of my data, or L of D, is just product of I equal to 1 through N P xi, or the P yi, given xi and given xi, right? And comma W, which will be just product of I equal to 1 through N, this normal distribution, which is here, W transpose xi sigma square. And we know what this is. This is just that standard Gaussian form. So this is how we compute the likelihood. And we also know what is the prior on W. So the prior probability of W, which is P of W, is this, right? Is normal sigma 0. And we know how to compute that as well. And then the posterior on W of W, which is the probability for W given we have seen the data set, right? That is, so posterior is likelihood times prior, right? So it is L of D times P of W. And then, of course, since we want to make them all normalized, so this is integral of L of D P of W dW, right? So we marginalize over all possible values of W. So in this problem, you can compute what is L of D, right? The log likelihood of your, or just the likelihood of your data. And you can also compute this part, which is the prior on W, because you just apply this here. In the problem, when we get back, I'll show you that I have given you what this is, I have given you what this is. So you know everything to compute the prior. Now to compute the posterior, you will multiply those two values. This will be like a scalar value, some point something. This will be another scalar value. So you can just multiply them together. This will be tricky, right? But what you will find is that, because in the problem I'm asking you to compare the posteriors, right? And this will be same for all W's. So you don't really have to compute this. You'll compute this for every W and let's just compare which one is highest. And just to make your computations a little easier, instead of computing this value, you can also compute just the log posterior, which will be log of L of D, which is the log likelihood, plus log of prior. And divided by some z, or actually minus some z, because this term will come in as a negative subtraction. But this you can ignore. Ignore if comparing. If you want the exact value of your posterior, then you will have to compute it. And for Gaussians, actually, it's not that hard, right? But for comparing, you do not. You just compute this, all right? So that's what you would do in this problem for that fifth thing, right? You would compute the posteriors for each possibility and just compare them. Question? I'm sorry. So L of D is the likelihood of the data. So let me tell you what that is. That is just the product of individual probabilities, right? So what is L of D? Likelihood. So that is, I've written it here. So it is pi I equal to 1 through n, right? The PDF of every yi. Now we are assuming that yi by itself is a Gaussian, right? Which means this will be 1 over 2 pi sigma times exp or e power minus 1 over 2 yi minus w transpose xi square sigma square. So we know what, so what you would do is you would basically, for every data point, for every yi, you know what yi is, what xi is, you know what w is, so you can, and you know what sigma is, so you can compute the whole thing, right? And then the product. Yes. This sigma? For W, all right. So what would be the sigma and mu? It need not be. So this is something that you provide. It's like a hyperparameter. Typically, just to keep things simple, we make it as a diagonal matrix, but it need not be. In real life, it need not be. Any other questions about this one? Okay, and then another thing that you want to sort of just to continue on this is need to understand about these regularizations, right? So regularization is another very important part that we studied. Is how do we force our solutions to be not too complex? So we looked at different types of regularization. Where is it? So we looked at ridge regularization, where we said that, okay, we are going to modify our objective function like this. We are going to say that J of W is yi minus W transpose xi square summation I equal to 1 through n, whatever here, we can put a 1 over 2 here, right? Plus we add another lambda W transpose W, right? And then I think in some parts of the note I've also written this thing as this 1 over 2 y minus xw transpose y minus xw, where y is a vector containing all yi's and x is the matrix, right? And they both are equivalent. These are both same. So if you remember, there was one gradients problem in which I had asked you to derive the value of w, which optimizes this, minimizes this, with different sort of constants here. So that was just for you to understand how the derivation is done. But I think in class I have done it for one setting, so you can easily extend it for other settings as well, right? But think about what the effect of this is. So what this does is that it actually puts a constraint on your w, right? It says that even if I might have a w that minimizes this very well, but if its total magnitude is very large, then ridge regression would not like it. So it would prefer solutions in which this part is also small, right? And how much that preference is determined by this lambda. And of course, in your programming assignment, you have done that too, great detail, right? Now the other thing is that, other thing that you want to sort of look at is that there are other regularizations as well, right? So there's one called lasso, right? Where you say that JW is this quantity, same as above, plus lambda, like just the sum of the mod of W. So L1 norm of W, right? So we call it the L1 norm. I didn't quite tell you how to solve this, because for this we need a little more mathematical background, because this is no longer a continuously differentiable function, right? Which is fine, but you do need to understand what is the effect of this, right? So if you remember, we said that what lasso lets you do is it makes some values of W non-zero and lot of other values zero. So it kind of does feature selection for you. So if you look at W and you just plot it like this, so this is W1 through whatever WD, what lasso will give you is that some values will be non-zero and everything else will be zero. So it also gives you some kind of a feature selection, because what it is telling you is that these three features are important. And that's why lasso is sort of useful. It does both. It does the regularization, which means that it ensures that your solutions are not too complex, but it also sort of brings things down. One more thing that you might want to, you should look at is the relationship between regularization and the prior, right? So if you remember, ridge is a regularization that we put on our loss function, which is equivalent to putting a Gaussian prior on W, right? Which is our Bayesian regression. Same way, lasso is equivalent to putting a Laplace prior on W. So sort of try to see this concept as well. Any questions so far? Okay. Now let me look at the next topic. So I said this, and then of course we talked about the whole thing, right? The regularization part, how is lasso related to Bayesian regression, and how is ridge regression related to Bayesian regression, and so on. Yes. Oh, so robust regression. Okay, that's a good question. So in robust regression, what you do is you do not put any prior on your solution, right? Robust regression is this. You say that my J of W is actually just summation I equal to 1 through n y minus W transpose xi. And you can put up 1 by n or 1 by 2 here. That doesn't matter. That's a constant. But instead of, so remember in least squares regression, right? This is a square here. Here it is a absolute term. You can add regularization to this, right? But in the, I think, yeah, that's sort of something that you can add here. May add regularization, but most of, I think the one that is in some of these Python libraries, they don't add a regularization, or at least they give you an option of adding it, right? But what will happen is that this, solving this becomes a little tricky again, because there is an absolute term here, but you could do it. There are ways to do that. But regularization is sort of an addition to this. So this robust regression should be related to least squares regression. So in least squares regression, we use a Gaussian, a squared loss. In robust, we use like a mean absolute deviation, so like a absolute loss. You could also relate it in a probabilistic sense, right? So in okay. So least squares, robust. So here you have y minus W transpose xi square summation. Here you have yi minus W transpose xi modulus, right? If you're looking at a probabilistic interpretation, in probabilistic interpretation you say that yi is a normal distribution centered at W transpose xi with sigma square, right? In the case of robust regression, you say yi is actually Laplace of W transpose xi. It only has one. So you use a different distribution instead of normal. But here we are not talking about regularization at all. Regularization comes after that. So you could add a ridge regularization to this and a ridge to this. It will become like a robust ridge regression. Or you can add a lasso regularization to this or lasso to this. So that's sort of orthogonal to that. Any other questions? Yeah. 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 Right. Not really, no, because see, this is the one you're talking about, right? So this is easy because we did one, and then we sort of, the only difference between all these four is the constant terms that are on the other side. If I give you a different equation, right, what you need to solve it is more mathematical concept. So I'll not ask that, right? Yeah. But in future, for your research, you should be able to do that, because all you do is you refer to matrix cookbook. Hopefully, that should give you the answer. Okay, any other questions about this part? All right, we have a few more minutes, or maybe no minutes at all, or 2 minutes, okay. So let me just talk about logistic regression. That's not too hard. So logistic regression, essentially the things that you want to understand is why do we call it a discriminative classifier rather than a generative classifier, and we have had that discussion before. So if you look at part C something slides, C3, part C2 slides where we talk about logistic regression, I have some discussion on, okay, why is it a discriminative classifier, right? And I gave that example in class about languages and how you want to differentiate between that. So check up on that. And then, of course, what is the difference between logistic and linear regression? That's clear. Logistic is for classification, linear is for prediction. But what you need to understand is how do we get to logistic from linear, right? So the only difference between logistic and linear is actually this. Instead of using normal, we say yi is actually Bernoulli on sigma W transpose xi, right? So actually least squares, robust, logistic, they all have some similarity. They all are doing W transpose xi, but then they're applying different probability distributions to get your yi, right? In the case of logistic, because we are assuming that yi is Bernoulli, that means it can take one out of two values, which means that it becomes a classifier. That is the idea. And then also look up some discussion on what is that, multi-class logistic, and that's something that you did in class as well in your programming assignment 3, is how do we convert a binary classifier into a multi-class classifier. And there are two ways, right? One is you do this one versus all thing, and another in which you do this straight method where you have one expression to compute the probability. All right, so I think we'll stop here, and then next class we'll talk about these 4, 5, 6, 7, 8, 9, 10 through 12. Okay, all right. Okay, so I'll see you on Friday. Thank you very much.